Yeah, good morning to all. It's my pleasure to introduce my younger colleague, Professor Debabrata Maiti, who did a master's with us in Department of Chemistry in, passed out in 2003. Then he moved to Johns Hopkins University for his PhD. Then he did a postdoc at MIT. And within a span of 8 years, he is returned to IIT Bombay as a faculty. Now currently is a professor. He's a very dynamic young leader in the chemistry. And in a short span of a time, he received several awards. If I keep reading his awards, I think that will take 15 minutes. He's already authored and co-authored 200 papers and several publications and so on. So every month I'll have to keep one mail ready to congratulate him for some or other award and with these things. So with this, with a short introduction, I invite Professor Maiti to deliver his lecture.
Hello everyone. Thank you, Professor Ravikant, for this sweet and kind introduction. Thank you, Professor Atre, and all the jury members for giving me this wonderful opportunity. Thanks all the colleagues and my co-workers, the members of IIT Bombay, who have been really supportive throughout our journey. Today, I'll discuss one of the work for which this talk I'm being selected for. Well, one of the biggest challenge I think our society faces today is to provide simple solutions for complex problems. And this is pretty much the mission of what we are trying to achieve in our laboratory at IIT. We are synthetic chemists. We try to convert simple molecule into relatively complex ones. Obviously, as all of us are aware, that enzyme can do some transformation effectively. But most importantly, enzyme can do these transformations very precisely and very selective manner. For example, in this slide, you see toluene, this on the left-hand side, simple molecule such as toluene, where you see that different positions are available. Selectively, only para position or the 4 positions can be functionalized by enzyme. There is yet another enzyme that is present where the same molecule is present and now not the para position, selectively this meta position can be functionalized. Now, as I was telling, enzyme is of course very special. Enzymes can do the transformation selectively, efficiently, but also it brings the limitation. And the simple limitation that enzyme brings is it can be effective on only few substrates, perhaps only one substrate, but if you may stretch it out, maybe it is applicable for few similar substrates. But the enzymatic strategy, usually as synthetic chemists, we find that these are not really widely applicable to a variety of organic molecules that synthetic chemists like us are looking at. So, to sum up what I'm trying to say, that enzyme transformations are excellent. It can do the job very effectively, but it can do the job for a selected few complex or selected few organic molecules. Synthetic chemists like us, I would say we are looking for every organic molecule. We are looking for making contribution or functionalization or making useful molecule out of simple molecules. Now, therefore, we need perhaps little bit different strategies by which an organic molecule can be selectively functionalized. Now, when we as synthetic chemists looking at enzyme and try to see the way enzymes are doing chemistry, if we can do the chemistry in our laboratory, perhaps that would solve some of the synthetic demand or problems that we are facing. For instance, if we look at the enzyme active site very closely, we find in front of the organic species, there is an enzyme active site which precisely picking up a particular position. For instance, over here, in this toluene molecule, despite having once again these at least 3 different positions, selectively this position is exposed towards the enzyme active site and therefore it is getting functionalized. Similarly, for the toluene molecule in this enzyme, although we have these ortho-CH and para-CH bond, selectively this position is getting functionalized because that position is exposed towards the metal side. So it's the perfect lock and key type of orientation we have in enzyme, but that sort of perfect lock and key combination in synthetic setup is not going to be easy. In every organic molecule, we have different positions available, different sort of carbon-hydrogen bond, let's say, are available. Of course, organic molecules are defined by the fact that they are made of carbon-hydrogen, and there are many different types of carbon-hydrogen bond, right? For simple benzene ring-containing molecule, as it's shown here, you have two different ortho-CH bond, two different meta-CH bonds, and one different para-CH bond. In the literature, even in the textbook, if we look at, we have ways perhaps to do the functionalization or the transformation at this ortho position. If you have a particular type of substituent, you can perhaps also do the reaction at meta position. In some cases, once again, if you have this particular X group, you can do perhaps the functionalization at the para position. But what remains really unsolved or truly challenging is, irrespective of the substituent, can you do this reaction selectively at any of these positions, such as ortho position, meta position, or para position? And also the type of reaction that one should be able to do in these cases should be versatile. That is something I would say remained more or less unexplored or very difficult to address. What we thought, can we look at the enzyme and try to come up with a solution for a variety of organic substrate, which again perhaps enzyme could not or did not solve, and perhaps it would be applicable for the simple organic molecule. In this context, what we were able to do simply is to take an organic molecule like this and was able to put a template or another organic molecule attached with it, which will hold a metal center precisely and effectively, so that only a desired carbon-hydrogen bond can be activated and subsequently be functionalized. Now, if you look at aesthetically, this is going to be similar to what we see in enzyme, because in enzyme, we have enzyme active site and the organic molecule is perfectly placed, and therefore, despite having many different carbon-hydrogen bonds, selectively one and only one carbon-hydrogen bond is getting functionalized. What we tried to design, once again, the major problem was number of reactions or variety of reactions at these positions could not have been previously done in synthetic setup by utilizing different strategies that exists already in the literature. What we were able to do, that we realized, first of all, that we need to overcome the limitation that exist in the method. And that limitations are, no matter what one's tried to do, we would end up having these proximal or so-called ortho-CH bond activation or meta-CH bond activation. To bring the activation of this distal or far away this para position, we designed this template. Once again, this is really been done by one of my excellent PhD student, Sukhdev Bagh. He just graduated, and she was the one who was able to successfully design. We have been working on this for several months and years, I would say nearly 2 years without much success. What we were able to show is simply, if we have a benzene ring and if we are able to attach this template, which is brown color in here, it will deliver the metal precisely at the para position. There were a number of features or number of characteristic features, design principle that went into making this template, which is brown color over here, successful. It ensures that the metal, which in this particular case we are using palladium, at least at the first instance, it will be held by this brown colored template. And due to its design, it will place the metal precisely at the para position. It delivers so precisely that other carbon-hydrogen bond that is present into the organic molecule remains intact, are not perturbed at all. What we realize that this design need to be absolutely perfect. If we change any parameter that you see over here, it's going to break down. For instance, we should not have any substituent at this position, which will restrict the movement. Also, the positioning of this linker has to be perfected. If we do anything else outside what is shown in here, the system or the overall reactivity as well as selectivity is going to be diminished significantly. With this perfectly designed template, which also has a pi stacking interaction between the benzene ring of the arene and the top phenyl ring of the biphenyl, we did a variety of reactions. This is one of such reactions where we show that simple functionalization such as olefination selectively can be done at this position. Once again, the other positions that is available into the organic molecule remain intact. This is a crystal structure of the product, which clearly shows that from the arene molecule, this template is coming out and wrapping it up and bringing the metal to the close vicinity of this para position of arene and making this approach sustainable and efficient. We subsequently diversified this template quite a lot. I'll not get into the detail, but by switching the atom connectivity, we were able to show that a variety of other organic molecule can be also incorporated. We were able to demonstrate that wide variety of pharmaceuticals as well as natural products can be synthesized in shortest possible route and in gram scale in many instances. We subsequently improved this template, which is brown color once again, by placing the suitable electronic and steric variant. And we understood that reaction mechanism works in a simple manner where metal is bound with the heteroatom and then subsequently selectively activate a desired position, not touching other positions, and then delivers the product. Here is another crystal structure showing how the organic molecule is placed with respect to the template, and then how the metal is coming and activating only one position, in essence giving similar orientation as we see in enzyme. Of course, by utilizing this, one can afford different pharmaceuticals, different chemicals, cosmetics, and other useful materials. With this, I would like to thank my students, particularly Shubdev, and to him. Of course, subsequently, the whole group was involved in development of this template and further utilization in several fields. And once again, I would like to thank IRCC IIT Bombay Professor Atre, and the jury member, as well as all my friends and colleagues here for listening to me. Of course, none of this work would have been possible without active participation from my group members, as well as my collaborators, all the funding agencies, DST, SERB, CSIR, as well as ISRO, DRDO are greatly acknowledged. Thank you very much. I'll be happy to have